Okay, so the final topic of the Stoichiometry chapter is on this concept of percent yield. And maybe because of our COVID-19 social distancing situation, you and your family may have been baking more. So the example that I always use when talking about percent yield is, if you're making a recipe for muffins or cupcakes or cookies, it will at some point in the recipe say how many the recipe is supposed to make. So the recipe is supposed to make 24 cookies. That would be what we would call the theoretical yield, how much this recipe should make. And then our actual yield is how many cookies you actually make. After taking the recipe and dividing up the dough and making the cookies and baking them, maybe you only had 20 cookies. Often what happens is in baking, it can be different sizes of the cookies, or, you may have taken a little taste here and there along the way and you don't have as much dough. In chemistry, there's a lot of things that can go wrong. Usually it's losing reactant in the process of transferring from one vessel to another. It can be what we would call side reactions, chemical reactions that were unintended. All those things can happen. So just like it says here, the stoichiometry problems that we've been doing, these calculations, tell us what should happen. But in the lab, we often do not get what we had anticipated. Okay, so what we often will calculate is something called the percent yield, which is going to be, I made 80% of what I should have made. I made 75% of what I thought I would make. So the actual yield is what you did in the lab. So this is going to have to often be given to you. And you're going to see words like, this is how much was made, this is how much was recovered, produced, obtained, removed. That was one I saw. So all these words could and are often used to describe what we call the actual yield, what is actually made. Now, the denominator, the theoretical yield, is what should be made. And I'm underlining the S here in should, because should means that you find that by doing, underlining the S again, a stoichiometry problem. So theoretical means calculated. Okay, so your theoretical yield is calculated. It's what you should make through, and you're going to calculate that through stoichiometry. The actual yield is what was actually made. So let's do a couple questions here and see what we get. So the first question says, carbon tetrachloride is a solvent that was once used in large quantities in dry cleaning. Because it is a dense liquid that does not burn, it was also used in fire extinguishers, but it was found to be a carcinogen, so we don't use it anymore. You use it for some very specific chemistry processes. I used it often in college, even though it's a carcinogen. So there's the balanced chemical equation of how you make it from carbon disulfide and chlorine gas. So the question says, what is the percent yield, right? Circle the do. If 719 grams is produced from the reaction of 410 grams of carbon disulfide. So what do? Read the question and figure out what those numbers actually represent. What a lot of students want to do is say one of those numbers is the actual yield and one of those numbers is the theoretical yield. That is almost never the case. It says if 719 grams is produced. So first of all, this is 719 grams of CCl4. That's a product in this chemical reaction is produced. It's telling you that's the actual yield. That was what was actually made. The second part of this, from the reaction of 410 grams of CS2, notice that CS2 is a reactant. That was not made. It can't be the actual yield or the theoretical yield. It's not a yield. It wasn't made. This is what I'm going to start my stoichiometry problem with. When we have questions that have a formula attached to them, we always write out the formula first. And that's actual yield over theoretical yield times 100%. And to keep in mind, we need to remember, this is the actual yield of CCl4 and the theoretical yield of CCl4. These will always need to be the same chemical, the same compound. Okay, we already know that the actual yield is 719 grams of CCl4. That's our numerator. We need to fill in our denominator. So we need to figure out, well, how much CCl4 should have been made. Where do we get that information? Stoichiometry, because it says I'm starting with 410 grams of CS2. Now, this is just a kind of simple 3 parentheses stoichiometry problem going from grams of CS2 to grams of CCl4. We've done this many times, right? 1 mole of CS2 is 76.15 grams, of course, in the periodic table. Then using the coefficients from the balanced chemical equation, 1 mole of CS2 will be used to make 1 mole of carbon tetrachloride, CCl4. And then 1 mole of CCl4, right? Because we want to find grams of CCl4. The molar mass for that is 153.81 grams. Oops, so I don't get this confused. I'm just going to write the answer down below, right? My grams cancels, my moles cancel, right? Grams of CCl4 is what is left. Multiply by the top, divide by the bottom. This number has 3 significant figures. These numbers have 4. Keeping in mind, I'm actually not going to round right here, but I just want to know how many significant figures I have. So right now, this comes out to be 828.13. Think about what that means. If I start with 410 grams of CS2, I should be able to make this much CCl4. I actually made 719 grams. So to find my percent yield, right, kind of think of this as like a separate problem over here. I take a 719 divided by 828.13 grams. And again, if these are not of the same compound, it doesn't work, right? We looked at this a little bit. If we're multiplying or dividing and we want the units to cancel out, they need to be the same exact units. Okay, so I'm going to divide those two. And then again, looking at the significant figures, 410 has 3 and 719, that would also count. My actual yield would have 3. So I'm going to round my answer to 3 significant figures. My entire units, grams of CCl4, cancel out because percents don't have like units of a chemical. It's not like 86.8% CCl4. This is saying during this process, I was only able to make 86.8% of what I should have been able to make. Okay? So we have a few more of these problems to try. And if at any time, you're like, yeah, I think I get it, pause the video, try the problem out, and then see if you get the right answer. Okay, so we're going to do, I think there's 5 more practice problems. Okay, if 67.5 grams of CCl4 are used in the reaction. Oh, and I said that. It's Cl2 are used in the reaction. So this is a reactant. So this is not my actual yield or my theoretical yield. This is what I'm going to start my stoichiometry with. And 39.5 grams of S2Cl2 is produced. That is my actual yield. And the question again is, what is the percent yield, right? Percent yield is the actual yield of the chemical S2Cl2 divided by the theoretical yield of S2Cl2. And I know the actual yield is 39.5 grams. S2Cl2. And I need to find the bottom of those. Let me smoosh in times 100%. Okay. So what am I going to start with? I'm going to start with my 67.5 grams of Cl2 and 3 parentheses to convert to grams of S2Cl2, right? 1 mole of chlorine is 70.90 grams of chlorine. According to the balanced chemical equation, 1 mole of disulfur dichloride needs 3 moles of chlorine gas. And then 1 mole of disulfur dichloride has a mass of 135.04 grams, right? Check everything, see if it works out here. Grams cancels, moles of chlorine, moles of chlorine, moles of S2Cl2, moles of S2Cl2. Multiply by the top, divide by the bottom, and we get 42.854 grams of S2Cl2. That is my theoretical yield. So 42.854, right? I'm not rounding right yet, right? I'm not using significant figures at this very moment. I'm going to wait a moment. Divide those two in my calculator, then multiply by 100%, and I get 92.2%, right? Both of the numbers that I start with have 3 significant figures, so my answer should have 3 significant figures, right? Thinking about what this question said, if I use all this chlorine, I should be able to make this much S2Cl2. This is how much I actually did make. I only made 35.9, which means my percent yield was 92.2%. Question 23. If the percent yield of the industrial process is 83.3%, how many grams of carbon disulfide, CS2, should be reacted to obtain 5.00 times 10 to the positive 4 grams of CCl4? And there's the second part to this problem. Every year I say I should cross that out. We just don't have, honestly, enough room in this space to answer that second part of the problem. And it's just another stoichiometry problem, so we don't really need to do that. So you can just draw a line through that. So this question's a little different, right? I'm giving you the percent yield. I'm asking how many grams of CS2 should be reacted. So am I asking you for an actual yield or a theoretical yield? Well, I'm telling you this should be reacted. Reacted means reactants. That isn't a yield. That isn't a product. That isn't something that was made. So I'm sort of asking you, like, what should I start my stoichiometry problem with? If the question says to obtain 5.00 times 10 to the positive 4 grams of CCl4, I want to obtain that. That's how much I actually want to hold in my hand. So this is my actual yield. And if you think about the formula, right, percent yield equals the actual yield of CCl4, in this case, over the theoretical yield of CCl4, of course, times 100%, right? Think about the fact that there's 3 variables in this problem, and you know 2 of them. You know the percent yield is 83.3. You know the actual yield, how much I actually want to make, 5.00 times 10 to the positive 4 grams of CCl4. I want to find, or I can solve for, the theoretical yield of CCl4. Now, if I figure that out, if I calculate that, you can think of it, go back, of taking the process that we just did and going backwards. Basically solving, down here, I'm going to solve for this. That's like solving here. And then I can just do a 3% stoichiometry problem to figure out how much of the reactant I should start with. Okay, mathematically, when we solve this problem, we don't actually, whenever we're using a percentage mathematically, we need to convert it into a decimal. That's like dividing by 100%, right? You don't need to write this step out because generally you don't. You just do 0.833 equals 5.00 times 10 to the positive 4 grams of CCl4 over my theoretical yield of CCl4. This is a problem that students have a difficult time solving mathematically. There's many different ways to solve it. It doesn't matter how you solve it. You just need to solve it correctly. So you can cross multiply here, but basically what you're doing to solve for your theoretical yield, you would take that 5.00 times 10 to the positive 4 grams of CCl4 and divide that by 0.833. Should come out to be a larger number. And it does. What does it come out to be? Oh, 60,024 grams of CCl4. So this is my theoretical yield. This is what I should try and make. It doesn't, in the problem before it, our theoretical yield was the end of the stoichiometry problem. Now our theoretical yield is going to be the beginning of our stoichiometry problem. Right? This number in my calculator, right? I'm not going to clear it because this has more significant figures, right? I don't want to round to the end. But now what I'm doing, look at what I'm trying to find. Look what I circled here, grams of CS2. So I'm basically going from grams of CCl4, 3 parentheses, to grams of CS2. 1 mole of CCl4, 153.81 grams. According to the balanced chemical equation, 1 mole of CS2 will be used to make 1 mole of CCl4. And of course, 1 mole of CS2 has a mass of 76.15 grams, right? Multiply by the top, divide by the bottom. The units keep on canceling. And my answer comes out to be 29717 grams of CS2. And then, you know what we got to do? We got to look at significant figures here. That green is hard to see. 3 significant figures in the 83.3. That does count. Those will count. 3 significant figures here. The numbers that the only other numbers I used were from the PRI table, and that has 4. So I should use 3 significant figures. So I could do 29700 grams of CS2, or I could put it into scientific notation, 2.97 times 10 to the positive 4 grams of CS2. Okay? We got lots of practice problems to do. Again, try these on your own, right? At this point in time, you may know how to do these problems on your own, right? And then check your work here. Question 24. This is a new balanced chemical equation. Calculate, this is going back to percent yield, for a reaction in which 0.38 grams of NO2 reacts. Right? We see reacts. That means that's how we're, STOIC. That's how, that's going to be the beginning of our stoichiometry problem, because this right here is recovered, right? That's a fancy way of saying my actual yield. So I'm going to start my stoichiometry problem, 0.38 grams of NO2, right? What do I want to do? I want to go from NO2 to N2O5, right? Because my actual yield and theoretical yield need to be of the same compound. That's always true. So 1 mole of nitrogen dioxide, 46.01 grams of nitrogen dioxide. According to the balanced chemical equation, 1 mole of dinitrogen pentoxide will be made from 2 moles of nitrogen dioxide, and the molar mass of N2O5 dinitrogen pentoxide is 108.02 grams. right? Making sure our units cancel out. Multiplying by the top, dividing by the bottom, 0.4460 grams of N2O5. What is that? That's my theoretical yield. That's how much should be produced, right? The question's asking for percent yield. I know that's going to be the actual yield of N2O5 over the theoretical yield of N2O5 times 100%. The actual yield was given to me in the problem, 0.36 grams of N2O5. The theoretical yield was 0.4460 grams of N2O5, and then, of course, multiply by 100%. Divide, multiply by 100. In this case, all the numbers that I have, the lowest is 2 significant figures. So I'm going to round this guy off to just 81% as the yield for that problem. Number 25, again, a little bit different, but in many ways very similar. What mass of N2O5 will result from the reaction of 6 moles of NO2 if there is a 61.1% yield in the reaction? What mass of N2O5 will result? See the words will result? This is telling me it wants to know the actual yield. N2O5 is a product in this reaction. So in this case, I'm solving for the actual yield. 6 moles of NO2. That's a reactant. That's what I'm going to start my stoichiometry with, and I have my percent yield, right? Percent yield is the actual yield of, what is the question asking me? N2O5, that's what I want to solve for, over the theoretical yield of N2O5, right? I already, or how many of these numbers do I know yet? Only one. I know that the percent yield is 61.1%. I know I want to solve for the actual yield, but I have enough information knowing that I'm going to start with 6.00 moles of nitrogen dioxide. I can do a stoichiometry problem to figure out how many moles of N2, or excuse me, how many grams of N2O5 I should be able to make. I'm already starting with moles of NO2. So that's a whole step that I don't need to do. Just 1 mole of, again, I'm going to N2O5 will be made from 2 moles of NO2, and then the molar mass of dinitrogen pentoxide, and that's that same number again, 108.02. Right, solving for this, I get 324.06. And what is that? That's the grams of N2O5. It's the end of a stoichiometry problem, which is how much I should be able to make. So that's my theoretical yield, right? My actual yield is still the numerator. The bottom is 324.06. So divide both sides by 100%. Basically just moves the decimal place over to 0.611. And then I multiply that by 324. So the answer to my question, how much will actually be made? 3 significant figures here, 198 grams of N2O5. Okay, last problem. I know it's been a long video. Last problem of the chapter, which means you guys know what the homework is tonight. It's the rest of the homework packet. That's right. So question 26, in the past, hydrogen chloride was made using the salt cake method as shown by the following equation. If 30 grams of NaCl and 0.25 moles of H2SO4 are available and 14.6 grams of HCl is made, what is the percent yield? This is limiting reactant and percent yield. The question again is asking for percent yield. It tells us 14.6 grams of HCl is made. The terminology is made tells me that that's my actual yield. So if I think of, again, the formula, percent yield is the actual yield of the chemical HCl over the theoretical yield of the chemical HCl times 100. I know the actual yield, that's going to be 14.6 grams of HCl. If I can figure out the theoretical yield, plop that in and then get my answer. How am I going to find the theoretical yield? Well, I have two reactants here, right? I have starting amounts of both reactants. So I need to figure out which one's going to run out first. The first step in these problems, if you do a BCA chart, if you do the three parentheses twice, every single time, the first thing you got to do is you got to convert both of them. You got to convert both of them to moles. So 30.0 grams of NaCl. Convert that guy to moles, 58.44. And that equals 0.5133 moles of NaCl, right? And then I usually use that first method that I taught you guys, where you label reactant 1 and reactant 2, and you sort of assume how much that reactant 1 was the limiting reactant, and try and figure out how much of reactant 2 you would need, right? Because this right here is how much reactant 2 I have. When I do that, I take reactant 1 and I convert it with 1 parenthesis to reactant 2. So 0.5133 moles of NaCl. Using the coefficients from the balanced chemical equation, 1 mole of H2SO4, that's sulfuric acid. We'll take 2 moles of salt, NaCl. And doing out that math, it's 0.2566. So 0.2566 moles of H2SO4 would be needed in order to use up all my NaCl. So the question is, can I use up all my NaCl? And the answer to that question is no, you can't, because I do not have that much sulfuric acid. In order to use up all 30 grams of my NaCl, I would need to have 0.256 moles of acid, and I don't. So my limiting reactant here is that sulfuric acid. So 0.250 moles of H2SO4. Now, right, I need to find the theoretical yield in terms of grams of HCl. 2 parentheses, right? 1 mole of H2SO4 will make 2 moles of HCl, right? If it's mole over mole, I get the coefficients. The coefficients from the balanced chemical equation are what I use. And then 1 mole of HCl has a mass of 36.458. Doing out that math, multiplying by the top, dividing by the bottom, I get a theoretical yield of 18.229 grams of HCl. That becomes, or that is, my theoretical yield of HCl. So I had to do a limiting reactant problem. Then I figured out which one was my limiting reactant. I figured out what my theoretical yield was. Divide those two. My answer, all these numbers have 3 significant figures with them. So my answer is going to have 3 significant figures. Divide and then multiply by 100%, and I get 80.1%. Okay? So lots of these problems. We're getting super good at doing stoichiometry, right? It's like our second nature here, doing all these parentheses. So after you watch this video, you can work on the rest of the homework packet. The answers to the rest of the homework packet will be up online, so you can check your work. And then this is your last video. Video number 3 is a percent yield problem. So take one of those 5 balanced chemical equations and literally just start making up the numbers. It doesn't need to be limiting reactant and percent yield if you don't want it to be. It could be like this one where I give you the percent yield, or it could be, this is sort of the traditional one where I ask you for percent yield by giving you the mass of one of the reactants and the mass of one of the products. Okay? You got to make sure that you choose a mass of product that will give you a percent yield that is lower than 100%. Sometimes you do get a percent yield greater than 100%, but that means that the sample has been contaminated. You've done something wrong. So generally in a laboratory, what we wind up with is percent yields less than 100%. We want to get them as close to 100% as possible, but that doesn't happen often in the real world. Okay? Work on the homework problems, ask me questions, work on your video, and stop in at any of the Google Meets to ask questions. Bye.